Good afternoon, everybody. Thank you for joining the meeting. Thank you for joining our webinar. Let's wait a few more moments if more people will join us. At this moment, I see 17 people being online on this meeting. I think they can catch up with us later. So let's get into it, because today's topic is quite broad, so we don't have much time to waste. Anyway, so I will now share my screen and start presenting the content which we prepared for you today. The topic for today is the fire analysis of reinforced concrete structures using ATENA. My name is Jiří Remeš. I will be your guide in today's meeting. Hopefully you can see my screen now. And yeah, it's kind of fulfilling my promise from the last time, when there were some requests to show how to use the results from transport analysis. At that moment, it was analysis of the young concrete during hydration, so there was heat development. In this case, it's a little bit different. It's the temperature distribution in the structure today will arise from fire loadings. However, then I will show you how to import the temperature data into the static module to conduct assessment for fire loading and structure response to this kind of loads. At the beginning, I will have a very brief introduction into the theory of this problem and into the important aspects of such an analysis in the ATENA software framework. And during that, and even meanwhile, and I will from time to time jump into our software to show you all the things we will be talking about directly inside of the software in the ATENA preprocessor and in ATENA Studio. So let me begin with explaining a bit about the overall framework of the analysis and the workflow of such an analysis. Today we will be dealing with two modules of ATENA. The first one is the transport module, where you simulate the fire loading and get the response, or get the results you will get is the temperature distribution in the model over the time of the fire. For this kind of analysis, we have temperature-dependent models, which have their thermal characteristic dependent on the temperature, and also we have a special boundary condition for simulating the fire load, which is used to prescribe the temperature evolution during the fire. Once this is done, you can review the data and import them into the static module. In the static module, this temperature distribution is converted into thermal strains that then act as a load on the model. At the same time, there are also temperature-dependent material models, which are used for reducing the material performance characteristics as a function of temperature, and therefore you can see how the material and the overall structure will respond to the applied load. The target output from the static module is then the fire resistance during the fire, meaning the time which the structure can resist to the applied load during some fire event, or it can be the residual load-bearing capacity after the fire event. These are the two most common outputs of such a fire analysis in ATENA. When we look into that as from the viewpoint of interval setting, in the transport module, it's quite easy. You will have one or maybe two intervals. The first one will be the heating, the increase of the temperature during the fire, and then optionally you can also simulate the cooling phase. However, after you import this temperature data into the static module, it's a little bit more complicated because you need to realistically capture the loading history. So probably before you apply the temperature, you need to load the structure with some self weight, some dead loads, service loads, and after that, if you input the temperature data, you can have an interval where you simulating the heating phase, and if you keep the temperature load constant, you will get the fire resistant times. Alternatively, you can simulate both the heating phase and the cooling phase, and after that, in the last interval, you can load the structure with some, let's say, prescribed deformation or prescribed loads to get the residual load-bearing capacity after the fire event. So these are the two main paths which you can follow during an analysis. In my example, which I will start dealing with shortly, I will go with this path where I have both the heating and cooling phase, and after that, the overloading of the structure. Before I get to the example, I would like just to quickly present the special boundary condition which we have in the transport module, which is aiming for fire loading. In this condition, you can choose from different type of curves based on available standards, or you can even use your own evolution of the temperature in time. I will show you this later. And this boundary condition will then ensure that at each calculation step, the temperature will increase or decrease according to what you have prescribed in the temperature evolution function, or what is actually defined in the specific standard. One note on the temperature dependent material models, as I mentioned before, they are both available in the transport module when they are used to automatically change the thermal conductivity and heat capacity as a function of temperature. And similar logic is used also in the static module, where there are function available, and actually in both modules there are some automatic tools to generate these functions, which are then used to reduce the material performance characteristics based on the temperature you import into the static analysis. So before I get any further, I think the slides can get a little bit boring over the time. So I will present the example. Today for the example, I prepared this kind of like a T-shaped beam. The beam is simply supported with a span of 2.7 meters. The total length of the beam is 3 meters. It has ordinary reinforcement for shear and bending, and on top of that there are tendons with this kind of shape used for press dressing. The press dressing is then transferred into the beam through the load plates at the end of the beam. And furthermore, there are load plates or supporting plates at the supports, and then in the two load plates in the span of the beam to apply the forces during the overloading. The fire event here is assumed as in the midsection of this beam along the length of 2 meters, and the fire will be applied from the bottom faces of the beam. Now, so far we have covered the easier part of the content, which is the transport analysis. So I will now go into the preprocessor and show you the relevant aspects, the relevant features directly in the software. Maybe, yeah, I should have mentioned at the beginning that that if there are any questions, maybe you can type them into the chat box, chat window, or into the if I hope there is a Q&A enabled in this meeting, or maybe I don't see it. I don't see the Q&A. So you can write the question into the chat window, and I will then stop and try to answer them. Or if we have time, we can have direct discussion at the end of this meeting. Anyway, let's now look into the software. So this is the beam I prepared. As you can see, now I'm in the transport module, and my workflow was that I firstly created a static model, and I tested without any impact of temperature to see how it behaves, to a little bit validate its behavior and to get some feeling for the model. And after this was done, I imported the geometry into the transport module. Therefore, you can see that I also have the reinforcement here. However, the reinforcement is not taken into account in transport analysis. So I will simply freeze these layers. This is the layer here called tendons and rebars. So now, if I actually display it again, you will see it as in a gray color because it's frozen. And only thing which I will have in my analysis will be the remaining of the structure. I actually also don't need the plates, and I only need the beam, and I have some monitors in my model. This one can be hidden, what I don't need. The monitors are placed in the cross section. Maybe I can show you like this, and the different position in the cross section, and in the transport analysis, I will use them to get the evolution of the temperature at these locations during the fire event. Another thing which I want to address now is the fact that I imported the model from the static analysis, and now it's the total length is 3 meters. However, I want to apply the fire load only in the midsection, only over 2 meters long midsection of the beam. One option which is possible would be to divide this overall volume into multiple segments, and then I will have a segment of 2 meters in length, and then I can apply the boundary function directly. However, now if I want to apply it for the 3 meter, it's not possible. I cannot define the boundary condition over some reduced length for the total surface. So So another option which I had and which I actually choose to show you today is to model another like a helping volume for me, which is only in this portion of the beam which I want to load by the temperature. I connected this volume with the beam using master-slave condition. For the beam, for the volume, I use different material. Here it's called conductive layer. The material, you can review it here. It's this material with ID number 9. It has a high thermal conductivity and at the same time very low heat capacity. So if once I will apply the fire load on this volume, it will not act as I will not. It does not have enough capacity to store the heat inside. However, it has high conductivity to transfer this applied temperature directly on the beam. Then I have other materials. It's a steel material, and it's actually for the plates. I can maybe activate them. And I have the concrete fire material, and in this concrete fire material, I'm using I'm using the temperature dependent material model. So in this model, I have some constant values of the thermal conductivity and specific heat capacity, and these values are then modified through these functions. In this temperature advanced variables tab, you can define different functions for the basic characteristics, and this function can then modify the initial value based on as a function of temperature or relative humidity or time. In this case, I'm using of course the option that this function, which can be reviewed here, modify the initial parameter as a function of temperature. So this is a relative function modifying the initial value given here. Actually, if if I go back to generator of the material, you can see that these parameters can be generated automatically based on the Eurocode. So if you choose the analysis type fire according to Eurocode 2, you can choose either lower limit or upper limit of for the conductivity definition. These are terms defined by the Eurocode, and you can choose the moisture content of your concrete, which is then used in the now it's just telling me that I will modify the parameter I had. Anyway, the moisture content is then used in this function. This is the function for the specific heat capacity, which has this kind of peak around 100 degrees C, which accounts for the latent heat of evaporation of the water, which is in the porous system of the concrete. So once we hit 100 degrees C, this water will evaporate. It needs some additional heat. So that's the meaning of this peak on this function. Anyway, now I covered the materials, and I will move to load cases and boundary conditions. These I already prepared. I already inputted into the analysis. I mean into the analysis file. I have prepared some load case for the support, which is used for the master-slave condition between this helping volume and the beam. I have a special load case for the fire. I have load case for initial conditions. This temperature load case is actually is actually not used. It will be used. It can be used if you want to directly prescribe the Dirichlet boundary condition, Dirichlet temperature on the model. However, I'm using this different approach using the fire boundary condition. And then I have some load case called non-insulated surface, which is actually in the analysis this top surface where I apply, even during the fire, I apply some ambient temperature, and then I have load case for cooling after the fire loading. In the boundary condition for fire, I have it. I already apply it. I apply it on this extra volume. As you can see here, the yellow color indicates where this condition is applied, or red color if I choose this option assigning or unassigning. And if I double click on the value, you will see that I'm using the option user curve. I adjusted the convection value, which supposed to be 25. According to the standard, I adjusted a bit to account for the extra layer. And I have this user curve with the temperature evolution. It actually looks like this. During the first 3,900 seconds, I have the heating phase. It's 65 minutes, I believe. And then until 2 hours, I have some kind of like a simplified linear cooling phase. So this function will be applied on the model. And so let's do it now in the task setting. So this task will include 2 intervals. The first one, let's call it heating, and let's set all the important parameters for this kind of analysis. So as I mentioned before, the first interval where I want to simulate actually the heating and initial cooling. It will span for 2 hours. So first 65 minutes, I will have the heating phase, and then until the end of the second hour, I will have the cooling phase. In this interval, I should have quite fine time steps. So I will choose 720 steps, which results in a step duration of 10 seconds. The transport analysis is usually pretty fast. It converges well, so I can have the luxury of having very fine time step. So in this case, I choose 10 seconds. I actually don't need to save each step in order to save my hard drive space. So I will choose to save only every, let's say, 6th step. This will mean that I will have results for reviewing every 1 minute. In case of fire analysis, we recommend to calculate only the temperature evolution, because here you can see the calculation type that you can choose from temperature and moisture, or just moisture, or just temperature. And when we include the impact of moisture, the analysis can get very complex. So and yeah, sometimes it's difficult to for example, prescribe correctly the boundary condition for the moisture transfer. So in this case, we advise you to only deal with the temperature analysis. And finally, I need to import the load cases which I defined. So it will be the load case support, it will be the load case fire, it will be the load case with initial conditions, and it will be the non-insulated surface load case which refers to which contains the boundary condition, which includes the boundary condition applied on the top of the beam. Now I will have a second load case. In this, I will call it prolonged cooling, and in this load case, I will simulate the cooling of the structure until let's say 1 day. So all the simulation is all the analysis covers 1 day. So the duration of this interval should be 22 hours. First 2 hours is my heating and cooling, and now I have the additional cooling. Now maybe I can my time step can be much coarser. If I have 88 load step, it will result that I will have results in every 15 minutes. Again, I only want to calculate temperature, and in this case, I will add supports, and I will have my load case cooling. In the cooling load case, I have a temperature boundary condition, which was discussed in the previous webinar. This temperature boundary condition automatically calculates the temperature flux between the model and the environment based on the environmental temperature and based on the gradient between the environmental temperature and the temperature at the boundary of your model. So this is my two load cases, and what I need to do now is to tell ATENA to export the transport results, which will be later imported into the static analysis. So here I can choose the names of my files, and this symbol at the beginning of the path, it just indicates that it should save them into the folder which is one level above the calculation folder. So with this setting, I think we are ready to launch the transport analysis. So I will save the load case and try to run it. You can see that the model was launched or the solution was launched in ATENA Studio, where I can now display the temperatures on the surface of my model. You can see that the temperature starts to increase. I can also already set the monitors. Let's monitor the the temperature evolution in the different parts of my model. Here I'm using the multiplicator to have the time axis in minutes. And here let's add the different monitors. I will just use now a few of them. Anyway, this now we have this ready. The solution runs. Now we are applying temperature of 76 degrees C, and I will let this solution run in the turbo mode, which can be used in here. And meanwhile, I will go back to my presentation. Maybe if there are any questions until now. Until now, no questions. So oh yeah, there are. Let's maybe yeah. So there is first question. Given that the temperature analysis is mass dependent, I assume using symmetry is not a good option to use in this case, right? Well, well, symmetry can be used in some cases. For example, because if I don't apply any boundary condition, it means that that this surface is perfectly insulated. So so if the problem is symmetric, it means that at the plane of symmetry, no heat is going through there because it's the same at both sides, right? So so in this case, I think symmetry can be used, but generally it's probably not necessary because the transport analysis is quite fast, so we don't usually we don't need to save that much time using symmetry. How does ATENA account for the temperature-dependent properties during cooling, both in the transport and static analysis? Yeah. So sure, the material doesn't restore its thermal or mechanical properties. Yeah, this is a good question, and it's different in the thermal and in the static analysis. In the thermal analysis, it's reversible. We actually assume it, although of course there is especially in the specific heat capacity function, the peak due to evaporation of water will not be there during the cooling. However, we don't have cyclic model for in the transport analysis. So this is a bit there is a slight it does not perfectly match what happens in the reality. However, in the static analysis, the mechanical properties are irreversible. So actually, I think it kind of agrees what is measured in the lab, that typically they heat the sample and then they measure the strength. So somehow we already input the residual strength in the analysis, and it will not be recovered during the cooling. So always the properties that are that correspond to the maximum temperature are kept in the analysis. And the last question: how does reinforcement account for the transport analysis? The reinforcement is ignored in the transport analysis. It's not there. So now let's move to the back to my presentation, and now we will be dealing with the static analysis. So at the beginning, I prepared some typical examples of the functions that are used in the transport analysis. These are the functions for strength and for Young modulus, and this is for thermal expansion. This is actually taken from I think from the Eurocode standard. In case you wonder why this is constant here, it's kind of, I think the idea behind it is that after some point the material is too damaged to be able to expand. So it's kept constant. However, one important note on this topic. Usually, when users develop their model in ATENA, we advise them to go step by step and gradually increase the complexity of the model, meaning that, for example, first you create a geometry, apply some elastic material properties, some simplified loading, and try to validate the behavior of the model to see if everything works correctly. And just after that, you for example, switch to nonlinear material models and go to more complex loading history. In case of the fire analysis, this is not always true, because, for example, if you import the temperature data and decide not to take into the account the reduction of the material properties and only account for the thermal expansion, you will get something which is probably the model and the solution will soon stop making sense, because if you imagine that the differential thermal strain applied over the model has this kind of distribution, but you will be still using the Young's modulus, which has no reduction in the value. If you look in here, I have some 10,000 microstrains, and if I apply them with 30 gigapascal, I get some unrealistic thermostresses, which does not make sense to use in the analysis. Therefore, when you decide that you use this kind of function for the thermal expansion, if you don't set it 0, then you should always use the reduction of Young's modulus to account for the to have realistic thermal stresses. Maybe the opposite way, when you neglect the thermal expansion and only account for the reduction of the material properties, and to see how this will to see whether the structure how it behaves under the loads only when you include the impacts of reduction of material properties due to temperature. That can make sense, but not the opposite way. Once you use the thermal expansion, you should always reduce the Young's modulus. This is actually a well-known phenomenon in this field. It's hidden in this mechanism of LITs, of load-induced thermostrains. This describes a behavior when a concrete is heated under unrestrained condition. When it's not loaded, it will expand. However, it will expand less if there is some load applied, because the material wants to expand, but however its material performance characteristics are decreasing as the temperature increases, so the expansion is not that severe. One famous experiment is shown here by Corey. This is the model in ATENA. It was cylinder with a diameter of 62 millimeters and a height of 186 millimeters. This is the data. Maybe I can zoom in here, and the data show when the load level was actually 0% of the compressive strength of the material, it's this curve, and when the load was 10%, it's this curve, and under 20% of the compressive strength, the expansion was let's say half of what the expansion was previously, under 10%. We actually try to simulate this one in ATENA. This is So of course, with the increased deformation, the results and a load of 20%. And during the heating phase, we obtained some reasonable match with the published data. Always the dashed line is the experimental data, and the continuous line is the ATENA simulation. So in both three cases, for the specific material they used, because this mechanism is quite material dependent, we were able to obtain quite a good match. So this was the case for the temperature dependent material for concrete. We also have temperature dependent material for reinforcement, and even you can use if you incorporate a bond model in your analysis, you can use a function for reducing the bond strength based on the temperature. Finally, this is my last slide. I have one note on mesh for fire analysis. Imagine that you are now simulating we have this kind of beam. The fire is on the bottom surface, so we can use this kind of mesh because it will be basically one-dimensional heat transfer. I can have a very fine mesh resulting in quite nonlinear distribution of the temperature during the cross section, because at the beginning we heat this surface. However, in this distance, the concrete doesn't know about any fire. It needs, the conductivity is not so high, so it needs some time to get some uniform distribution of the temperature. So if I then go to static analysis, I obviously cannot use this kind of mesh because the aspect ratio is wrong. And if I want to have the aspect ratio correct, I will have a very fine mesh and very difficult, very computational expensive. While because in static analysis, actually what I need is like maybe 6 elements per the thickness of the beam, per the height of the beam. So maybe something like this. And now I want to import this kind of distribution of the temperature on this mesh. So what will happen is that I will, assuming that I have linear elements, I will have this kind of distribution of the temperature, and eventually this kind of distribution of thermal strains on the cross section. Now you can see that all area where compared to this, this is the thermal strains that are not realistic. This is actually overestimation of the thermal strains and overestimation of the loading on the model. So this can lead, it's of course from the, let's say, perspective to be on the safe side, it's fine. But if you then start to debug the model and for example want to compare it with an experiment, you will see you may find that the damage is too high compared to what happens in reality. So maybe one option would be, if let me assume that I have reinforcement somewhere in here. So in that case, I can maybe separate the volumes of the beam and use some finer mesh below the reinforcement, maybe connected with master slave condition, or so I can have actually this kind of shape of elements. It will not be so good from the static view, from the viewpoint of static analysis, but it will be in this case the load transfer mechanism is mainly through the reinforcement and the concrete over here, and this acts more loading on the model. So in that in that case, I can have very precise approximation of the thermal strains during the fire if I adjust the mesh like this. So this is my hope this was a little bit somehow understandable. This was my final note and my final slide, and now let's check the calculation which is running here. So now you can see that I have. I will stop it now. It will be better for the post-processing. Maybe increase the font size a bit. So now you see that we are in the phase of the fire where the temperature is about 770 degrees C. You can see that that there is that the monitors which are closer to the surface, they show higher temperature. The monitors, of course, that are more further away from the surface, they show lower temperature. Now I'm able to post-process the data, for example, create cuts through the model, see the distribution, etc. However, I believe we somehow covered this one during the last webinar. So since the time is time goes fast, let's move to the static model. I have the model already here. This model, of course, uses there is no frozen layer. It has all the features needed, including the reinforcement. In this model, I use the concrete material model. The prototype is the nonlinear cementitious 2 material with temperature dependent material properties. And these temperature dependent material properties are given in this extra tab, where I can review each of them individually. I can adjust the function if I have that data for my specific concrete. In here, you can see the relative function multiplying the function constant written here. If I want to show it in the chart, I can choose here multiply by constant, and then I can see the absolute function. There is also a tool which can generate the temperature dependent functions based on the type of aggregate. This is again based on the recommendation by Eurocode. Similarly, I have the material with temperature dependent material properties for reinforcement. Here in the tab, I have the multiplier for the strength value. It scales the function in the y-axis, and I have the function for the thermal strains. I think what's now the most important is what to do is to set the task. The boundary condition in here are not so complicated. I have multiple master-slave condition to connect the load plates on top, the supporting plates, and the plates at the ends. I have function for applying the pre-stressing. I have boundary condition for self-weight, and then I have boundary condition for loading by force, which is applied on these two load plates. If I display the boundary condition, you can see them now. This is it's really not anything tricky. One thing which may be useful is that at the beginning I assign very soft material to these load plates, and the reason is that I don't want them to strengthen, to constrain my concrete material during the fire. And just after the fire, I exchange the material in these load plates to simulate, to have realistic steel plates during the overloading of the model. So let's get into setting of the task. So in first interval, I want to apply, let's say in 10 steps, I want to apply the supports, including the master slave condition. I want to apply the self-weight, in here body force, and I want to apply the pre-stressing. Maybe I can do it in 10 steps. It should be good enough. Actually, it's post-tensioning. Or I can. Another option would be to have it in 2 intervals, but I think it's good enough to have it in a single one. So this is my my step number 1, and after that I can simulate the fire. Let's say fire for 2 hours, so it will be including the cooling phase. For this interval now, I should import the temperature data. So in this tab called transport, I will choose the path to my temperature data. Actually, that will be this one which I calculated previously. It's not from the webinar. So one file, it carries the information about the temperature distribution, and the second one carries the information about geometry. As maybe not specifically mentioned at the beginning, but somehow I hope it was obvious that the meshes in transport and static analysis does not need to be identical, because ATENA will automatically interpolate the data in the space to in case the meshes are different. So now I chose the path with the transport data. Because it's not in the same folder as my model, I have this kind of yellow warning, but it's just a warning. It's I believe everything is fine. And of course, I want to have supports during this fire loading, and I need to choose how to import the data. There are 2 basic options. If I choose it importing each step, ATENA will import the transport data, each solution step, exactly as they are in the transport analysis. If I choose interval beginning, ATENA will look what is the temperature difference at the beginning of the interval and at the end of the interval, and then gradually apply this temperature difference through the multiple steps of the given interval. So it's more like incremental load, while the option importing each step is better for the nonlinear problems where I need to have the exact temperature history as in the transport analysis. So I'm choosing each step, and now in this import of transport data, I can adjust, and I should adjust the time that the time interval which I want to import from the transport data. The predefined data, the predefined options, those are based on the calculation step. So my first step now in the second interval is step number 10. The last step is step number 15. So this is the default, but of course I want to adjust it, and I want to go from time 0 in the transport analysis until the time of 2 hours. There is another time definition in which is used for the static task. However, this time definition is not specifically used for importing the transport data. However, to have it nice, I can say that this interval also duration of this interval is also 2 hours. And to have this first step negligible, I will use some very short time. This is just for my convenience when post-processing the data. I'm sorry. I see that we are reaching to the end of the initial planned meeting. So I hope at least some of you can stay a little bit longer. The rest of you will have the rest of you who need to leave now, I'm making a record of this meeting, and later it will be available on our YouTube channel. So sorry for taking a long time. It's a long topic. Anyway, let's continue. So the second interval is fire and cooling, and third interval will again use the supports. It will again will be used for importing the data. Now, from the let's say from the time of 2 hours until the time of 23 hours. So the duration is 21. Here I forget to set the number of steps. The number of steps in this analysis, it should be again quite fine, because you want to simulate the problem quite. It's quite nonlinear, and the damage is accumulated quite quickly during the fire. So in order to have stable solution, you should have fine time stepping. So in this case, again, I will calculate it each 10 seconds. So I will have 720 steps. Probably I don't want to save all of them. So again, I will save the results for my post-processing only after each 1 minute. This step will be called cooling, and again, I can now have coarser time steps. So every 15 minutes, I will have 1 step. And in the last interval, during the last hour of cooling phase, I will simulate the overloading of the model. So in this case, I want to apply the supports. I want to apply the forces. That's the load case where I have the force load. Yeah, and actually I want to import the data because it will happening during the last hour from the cooling. So I'm starting 23 till 24th. This is better. So overloading. So this is more or less the analysis setting. What is remaining is to set here some duration and some appropriate number of load steps. Now, because the load will be applied, so typically for this kind of analysis, maybe 100 steps or can be appropriate. And here, this was a mistake. Of course, here should be 23 hours. Before I launch the calculation, I want to have a quick note on the solution parameters. The calculation of the fire load typically results in high damage in the material, in a lot of cracking of the material. So based on our experience, is better to directly use more stable solution parameters. So typically not to use the tangent predictor, not to use the full Newton-Raphson method, but to switch to the modified Newton-Raphson method, meaning that we will use the elastic predictor. The modified Newton-Raphson method typically needs more iterations to converge because the stiffness matrix is not inverted in every iteration. However, from the same reason, because there is because the stiffness matrix is not the inversion of the stiffness matrix is not done in each iteration. It saves some time, so each iteration is much faster than when using the full Newton-Raphson method. So at the end, the total solution time is more or less the same. In this case, I will use, let's say, maybe 300 steps. I actually don't, when I'm using the elastic predictor, I probably don't want to use the line search method. And and I would like to bring your attention to this window where you can set the option for using the iteration with lowest error in case of when the convergence is not reached after the 300 steps. When I input here number 10, I will now increase it to 25. ATENA will search through the last 25 iteration to find the one with the lowest error and then proceed and continue with the analysis using the results of this iteration with the lowest error. So this is my solution parameters. I will these I can then use in the setting of the interval in here. I will now not launch the analysis because we don't have time. Again, I'm sorry for running late, but to show you a bit of the post processing, I have the data here ready and calculated. So I calculated in advance this problem. You can see all the steps in here. And my favorite way how to open this kind of set of data is to open the input file in ATENA Studio. Then you can see it here, then switch into the post processor, right-clicking in this window and scan for results. Now I get a message that there are some results fine. I want to read them. And now ATENA Studio will automatically detect the data and show me the model in here. For the quick post processing, I will go to step number 400. That's the peak load from the fire analysis. The data are red. I will show. So let's see how the fire affected the concrete. You can see many thermal cracks in the model. Probably there are too many of them, so I will set some filter to crack off the width of 0.1 millimeter. Now we can see that they are somehow more localized. I can maybe create an activity to show only the concrete. I can maybe show the deformed shape. This is too much. So you can and see what is happening. I will plot here the time, and I will plot the displacement in the midspan. I have monitors for this ready. So again, let's adjust the monitor, the time axis to have it in hours. So now I'm here in those 65 minutes. That was my peak load. I can plot the crack width. Now there is an option to plot the maximum crack width, not to plot the width of each principal cracks, but to plot the maximum amount of them, which is useful, especially for this kind of analysis, when the maximum crack is not always the first one. And maybe I can also adjust the scale a bit. So what this results indicate? So I have some localized crack on the top flange. They have spacing which is approximately in the range of the spacing of the reinforcement. And I have here the concrete which if I even increase the deformation, it show the tendency of spalling. This is again the concrete which is close to the bottom reinforcement. I can see how the deformation of the sample evolved during the loading. Typically these change in the tendency, in the trend, it indicates some crack opening. So basically the model wants to behave wants to bend some way due to the thermostresses. However, at certain point, these thermostresses exceed the strength of the material, crack deforms, and it can change the trend of the behavior. maybe I can now so this was very quickly showing showing some results. If I go at the beginning of the fire of the fire, let's say step number 70, that should be 10 minutes of the fire. You can see that the cracks are not yet so big. There will be some cracks if I release the filter, but they are not opening that much. After 20 minutes, you can see that this this area at the bottom in actually the cover distance from the reinforcement starts to crack, and then at the end of the fire, at the moment of the maximum temperature, these cracks grow significantly. Again, I will now apply the filter. One thing which also might be informative at this moment is to plot this parameter, which is now new in the latest release of ATENA. It's called yield crash info, and it tells you on which stage of the compression branch of the material we have the plasticity approach. So we have the elastic range. Then we have some yielded point and hardening until the maximum compressive strength, followed by softening. So actually, now I can plot this parameter with standard value, and if the value of this parameter is 1, it means that the concrete is crushed. So how it wants to expand, it's during the fire, it's subjected to compression stresses, and then it crashes. So actually, this somehow now nicely corresponds to the areas where the spalling of concrete occurs. So actually, I can now set a volume limit on this parameter. So it's either 0 or 1 if I plot it in element nodes. And now, if I want to see where is it above 0, I can only see the elements where the concrete is in the softening regime. So meaning it's crushed and the strength is going down. The stress is going down, and this area, they correspond nicely to the spalling areas. Now, when I will move to the moment just before application of the overloading. I see that many people stayed here. Sorry for going too long, and now I'm actually happy that I'm not talking here just for myself. So yeah, of course, during the heating, there was still during the cooling phase, there was still some damage. You can, on the deformed shape, we can see more material. Try to somehow being crushed and showing this spalling tendency. I will move back to displaying the Craig width. And I need to reset this filter. And I will adjust the scale a bit. Okay. This is better. And yes, so just to just to finish the talk for today, I will show the last step of the analysis, and I will plot the load displacement diagrams. Before it was the evolution of the displacement during time. So now I will plot typical load displacement diagrams. So I have here monitors for here, and this is, and probably have this one in millimeters, and to have the load in kilonewtons. So this is here we can see the end of the fire, and at that moment the sample was bended upwards, and from this moment I started to applying the load on these two load plates. We can plot them on these two load plates, and the beam was bending downwards until I reached some maximum capacity here around 175 kilonewtons. After that, we see failure of the specimen. So this will be my residual load bearing capacity of this model. So yeah, I'm already 20 minutes late. Sorry for that. However, if you now still have some questions, I will be happy to answer them. Bogdan is asking, can you show us how to change materials in different tasks? Oh yeah, I forgot to mention. So as I was explaining maybe a little bit quickly at the beginning, I have this load plate simulated as soft elastic material. The reason is that I don't want them to strengthen the top flange of my beam during the fire event. However, I need to have them as steel during the loading. So I have here two materials. One is steel elastic and another one is soft elastic. At the beginning, I'm using the soft elastic, and at the fourth interval, when I simulate the overloading, I can activate here this option construction process, and here I can specify what material I want to what is my what elements I want to exchange. Actually, here it's not distinguished based on the material name, but based on the name of the building element type. So I have here also two building element types. One is a plate which uses the steel elastic material, and another one is the soft plate which uses the soft elastic material. So here in the fourth interval, if I go to the construction process setting, I will be changing the element type called soft plate. I will I will change it and reset, and I will use the plate material. So this is all I need to do. All I need to do to ensure that the material will be exchanged. If I can check that it really happened in the post processor, because now I can here see the material still elastic. That's after the exchange of the material. However, if I go somewhere at the beginning of the analysis, just a second. I should. So maybe in this analysis I didn't do it. There should be the soft elastic material written here. Oh yeah, actually it's here. It's this soft elastic, because the end plate, they use the steel elastic, the one with realistic properties, and only for these top plates I use this soft elastic, which is now written here. Okay, is there another question? Okay, so there are no more questions, which I can see. If so in that case, we can conclude the presentation.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.